Hi, my name is Josh, and I'm the software lead on the Caltech robotics team. I'm joined today by Sandra, and we'll be discussing some of the improvements we've made to our sensors over the past year. I'll be talking about improvements to our vision system, but first I'll hand it to Sandra to discuss hydrophones.
Hi, I'm Sandra, the electrical lead of the robotics team. I'm a rising junior majoring in electrical engineering, and today I will be talking to you about the developments made on the existing hydrophone system in an effort to allow for inter-sub communication. While the subs are expected to complete different tasks from year to year, an essential task is detection of pings using a hydrophone array. Our existing hydrophone array, as seen in the figure, has already proven to be successful at detecting the ping signals, as well as processing them to deduce the pinger location. With the recent allowance of 2 subs in the water, we decided to use this remote ear to venture into the possibilities of inter-sub communication. There were many considerations that had to take place. The first and most important one was how to prevent the 2 subs from crashing into each other. Another decision was what communication channel type to use. We ended up choosing an acoustic channel, since other options such as RF or optics don't work as well underwater. The trade-off is that acoustic channels have low wave speeds, around 1500 meters per second, which means Doppler shift is a problem. Another drawback is that there are many potential interferences, for example, from walls, the other sub, and even the pinger itself. With all these factors being main concerns, we proposed a problem statement as follows. We want to design a communication system that allows the subs to communicate their position to each other, does not interfere with the pings, is robust to noise and reflections, and lastly, communicates as fast as possible. So to progress this effort, we first used the NumPy Python package to develop an emulator that simulated the transmission of signals between 2 subs in motion. The emulator simulated the full channel, modulation and transmission of the signal from one sub, and detection and demodulation of the signal on the other sub. This allowed us to see how the movement of the subs shaped the waveform from transmitter to receiver. It also let us test various communication schemes and design our hardware around those that worked best, since the simulator indicated which schemes had more bit loss and desynchronization at higher bit rates. So far, we have tested differential quadrature phase shift keying, or DQPSK, frequency shift keying, FSK, QPSK with 2 simultaneous frequencies, and orthogonal frequency division multiplexing, or OFDM. OFDM showed to be the best with regards to having minimal desynchronization issues, and thus reducing bit loss. The next steps for the emulator include accounting for deformation of the signal caused by, for example, reflections off surrounding surfaces. With regards to transmitter implementation, the current design mainly consists of a microcontroller, a direct digital synthesis, or a DDS, filter and amplifier, and lastly, the hydrophone transducer. Another option to replace the DDS would be to use a phase lock loop. We chose a DDS for its better frequency agility and its improved performance of phase control under frequency switching. The latter reason is especially important since we will be heavily relying on frequency or phase modulation, whichever ends up being best from the ongoing emulator testing. So we want to make sure to transmit a modulated signal that is as precise as possible. The modulation is done with the microcontroller, and then the DDS will convert the digital output to a corresponding sine wave.
Visual perception is an essential part of a competitive robot. Almost every task involves aligning the sub to a game object, and these game objects are most often easiest to sense by their visual characteristics, usually a distinct color or a decal of some kind. Our vision system has to help our sub through every phase of the task. That means it must assist us with first navigating to the general task area, then aligning with the particular game object, and finally verifying whether we have completed the task successfully. Each of these steps gives a corresponding requirement for a successful perception system. We must be able to perceive objects at long distances to assist with navigation. Once we're closer to the object, we need detailed detections that provide linear and angular transformation information to perform alignment maneuvers. And finally, we should ideally be able to differentiate a complete task from an incomplete one. Like any sensing system, we also want guarantees of reliability from our detections. For visual perception, this requires functioning under varying lighting and water conditions, such as from the time of day or cleanliness of the water. We of course also want to be sure all our detections correspond to actual game objects, and that we find all such game objects in the camera frame. Finally, our system should be fast. Slower updates lead to worse performance as camera frames become outdated and control loop time steps expand. This can be a particularly challenging requirement, as many techniques require strong hardware or software optimizations to run adequately often. There are two main categories of objects we want to detect, those identified by decal images and those identified by a bright color. The traditional approach to recognizing decal images is to retrain an off-the-shelf neural network object detector to the specific set of images for the competition year. A challenge with any learned approach is that our dataset must include all conditions we want our detector to perform within. Without the opportunity to gather data on the transdeck itself, adversarial image augmentations, including blurs, dims, and color shifts, become critical additions to traditional augmentations, such as affine transforms, to emulate different environments in the dataset. The major downside of these off-the-shelf detectors is that they only provide an axis-aligned bounding box for each detection. For many game tasks, this is adequate, but in others, such as torpedoes, we require a surface normal to which we can align the sub. This usually requires a contour of the decal to which we can apply geometric pose extraction techniques from traditional computer vision. To address this, we've developed a detector that learns the contours of the decals directly by detecting their corners in the image, allowing us to perform precise alignments without relying on less robust, hand-tuned techniques. The second major class of object is identified by a distinct color. Here, the typical approach is to use techniques from traditional computer vision. A detection pipeline might consist of the following: blur, transform to an appropriate color space, apply a static or adaptive threshold, dilate and erode to eliminate noise, extract and optimize contours, eliminate false contours via shape heuristics, and finally extract pose information from the remaining contours. These are staple techniques because they are easy to develop and extremely fast on modern hardware. Also, the near pixel precision of the initial detections provides ample opportunity for pose extraction. Unfortunately, their flaws are quite significant as well. Each operation has many parameters which must be tuned by hand, and this leads to brittle detector code that often breaks at the least opportune moment in competition runs. This is especially true because we can't tune for the transdeck ahead of time. We can break this pipeline into two parts. The first extracts colored clusters from the image, and the second operates on the contours of those clusters. While the first part operates on color information that varies with the environment, the second part operates on the expected shapes of game objects, which remain constant. As we would then expect, most tuning issues originate in the first half. To address the issues with tuning color detection, we've developed a neural network-based color cluster detector based on semantic segmentation techniques, which apply a class to every pixel in the image. To do this, we retrain an off-the-shelf, real-time implementation of semantic segmentation to instead operate on color classes. Combined with a robust enough dataset, this ensures that our color detection works across all lighting conditions in both our practice pool and the transdeck. A key advantage of this approach over an end-to-end machine learning solution is that colors are reused every year, so data gathered in prior years remains useful for training the detector. The output of the network looks exactly like color detections from traditional techniques, so it also slots nicely into the traditional vision pipeline, allowing reuse of our already developed pose extraction techniques. Gaining confidence in a perception system requires testing it in a wide variety of conditions, necessitating a large dataset. Moreover, large amounts of data are required to employ learning-based approaches. To gather this data, whenever we have a camera in the water, we save a subset of the captured frames into ROS bag files. With a large backlog of data, it becomes possible to test and tune new methods entirely offline, a requirement for any methods with lots of manual parameters. A unique challenge for detecting any year-specific objects, especially with machine learning methods, is that we lack data from the transdeck until the competition itself. Were we simply reusing detection methods that have generalized to the transdeck in the past, this would be less of a concern, but it's a critical issue when altering the operation of the detection pipeline. To address this challenge, we evaluate new methods by training them on practice data and testing them against the transdeck data from that year, rather than just on their performance in practice runs. The ability to generalize on prior year's data gives us confidence that our detectors are likely to work on the first day of competition in the coming year, or will do so with minimal changes. Another strategy we employ is automated regression testing. We maintain a list of scenarios, pairs of images and their expected detections, in which each detector must perform, and we regularly run offline tests against these scenarios. For instance, we might verify that a torpedo opening detection is found within the bounding box of the board itself. This is especially important for manually tuned methods because tuning for a newfound failure case will often hinder performance in other critical scenarios. The regression suite surfaces these issues before we put the sub in the water, which drastically decreases iteration time when tuning. The key to this approach is that we add new failure cases as we encounter them to ensure detector performance consistently improves.